Hi everyone, welcome back to my videos. I like to do a tutorial on arc congruence theorems. So let's start off with this first theorem. Given a circle of center O, angle 1 and angle 2 are inscribed angles, and they both intercept a common arc CD. So angle 1 is here, angle 2 is here. You can see that they both intercept this same arc. So prove that angle 1 is congruent to angle 2. So write down what we know, and we know that measure of angle 1 equals 1/2 times the measure of arc CD, right? Because it's an inscribed angle, so we have a formula for that, right? And measure of angle 2 equals 1/2 times the measure of arc CD, using the same formula, right? So we see that these two quantities are equal, so measure of angle 1 equals measure of angle 2, and therefore angle 1 is congruent to angle 2 by the definition of angle congruence, and using what we have in statement 6. Okay, theorem 2. Given a circle center O, angle 1 and angle 2 are inscribed angles, and angle 1 is congruent to angle 2. Prove that arc BC is congruent to arc EF. So write down what we know. And we know since angle 1 is congruent to angle 2, then the measure of angle 1 is equal to the measure of angle 2 by the definition of angle congruence. So using the formula for inscribed angle measure of angle 1 equals 1/2 times the measure of arc BC. Measure of angle 2 equals 1/2 times the measure of arc EF. Therefore, measure of arc BC equals measure of arc EF, since measure of angle 1 equals measure of angle 2, right? So we can use the definition of arc congruence and the fact that we're dealing with the same circle here to get arc BC is congruent to arc EF. So theorem 3, given a circle with center O, triangle ABC is inscribed in the circle and side AC is the diameter. Prove that angle B is a right angle. So write down what we know. An angle AOC, this angle here is a central angle, right? Because angle AOC has its vertex at the center of the circle. The measure of angle AOC equals 180 degrees because this is a straight line, right? Straight line, straight angle means its measure is 180 degrees. So the measure of arc AC also equals 180 degrees because the measure of an arc equals the measure of its central angle. Angle B is an inscribed angle, right? Because its vertex is on the circle and its sides are chords, right? A chord is a segment joining two distinct points on a circle. So measure of angle B equals 1/2 times the measure of arc AC by the formula for measuring inscribed angles. We can use substitution to get measure of angle B equals 1/2 times 180 degrees, right? And that's 90 degrees. So angle B is a right angle since a right angle measures 90 degrees. So theorem 4 is not as important as the previous theorems, but I'll go over it anyway. So given a circle of center O, segment PA is a tangent segment. Segment PB is also a tangent segment. Prove that the measure of angle P equals 180 minus the measure of arc AYB. So write down what we know. And angle P is a tangent angle, right? Because angle P's vertex is outside the circle and its sides are tangent segments. So we can use the formula to measure tangent angles, this formula right here. And we also know that one rotation of a circle measures 360 degrees. So we can add these two arcs together, right? I mean, technically I should also, right, use the arc angle postulate in the reasoning, but we'll just keep it simple. So measure of arc AXB plus measure of arc AYB equals 360 degrees. So we can substitute. So if we know measure of arc AXB is going to be equal to 360 degrees minus measure of arc AYB. So if I plug that into this formula we have in 3, we get this, and then we do some simplification, and we get measure of angle P equals 1/2 times, in parentheses, 360 degrees minus 2 times the measure of arc AYB. Well, if you do a little bit of algebra and simplify it, you get measure of angle P equals 180 degrees minus the measure of arc AYB. So that's exactly what we want to prove. Okay, so let's go over some examples. The first example, we have a circle center O. segment BC is congruent to segment DA. Prove that triangle BCA is congruent to triangle DAC. So write down what we know. We know the measure of angle B, this angle here, equals 90 degrees, and also the measure of angle D also equals 90 degrees. Why? Because an inscribed angle whose sides contain the endpoints of a diameter measures 90 degrees. So we saw that, right? When you have an inscribed triangle and one side is a diameter of the circle, then you know you're going to have, the inscribed angle, one of the inscribed angles is going to measure 90 degrees, right? So angle B and angle D are right angles, right? Because an angle measuring 90 degrees is a right angle. Therefore, triangle ABC and triangle CDA are right triangles, right? Because a triangle of a right angle is a right triangle. And then we can use the reflexive property congruence. Segment AC is congruent to segment CA, right? And then we can use the hypotenuse leg postulate since we're dealing with right triangles. So we get triangle BCA is congruent to triangle DAC, which is what we want to prove. Okay, so example 2, so we're given a circle of center O, and we're given a circle of center P. We're given the measure of arc FC equals 170 degrees, and the measure of arc EB equals 30 degrees. Find the measure of arc AD. Well, this is kind of an interesting problem, right? Because we don't know anything about this circle, right? Any details. We know stuff about this circle, so we're going to have to find a way to connect information between these two circles. So let's take a shot at it. So angle 1 is a secant angle. So measure angle 1 is here, right? And angle 1's vertex is outside the circle, and its sides are secant segments, right? And a secant segment intersects a circle in 2 points, right? So you see that point EF, and then down here another 2 points B and C. So the formula for measure, if you're dealing with a secant angle, is measure of angle 1 equals 1/2 times, in parentheses, the measure of arc FC minus the measure of arc EB. So we can do some substitution to get measure of angle 1 equals 70 degrees. Now let's take a look at angle 1 and angle 2. Well, they're vertical angles, right? So they're congruent. So angle 2 is congruent to angle 1. So the measure of angle 2 equals the measure of angle 1 by the definition of angle congruence. And then we can use substitution. We know measure of angle 1 equals 70 degrees, so the measure of angle 2 equals 70 degrees also. Angle 2 is a tangent angle, right, for this circle, right? Do you see that? And then we can use this theorem 4, right, where, let's go back here. So this theorem here. So measure of angle P plus measure of arc AYB equals 180 degrees. I didn't write it that way, but that's the same thing, right? If you just put this term over to the left side of the equation. So in other words, measure of angle 2 plus measure of arc AD equals 180 degrees. So we know measure of angle 2 is 70 degrees, so what's measure of arc AD going to be? 110 degrees by substitution. Okay, so example 3. Given a circle of center O, triangle ABC is inscribed in the circle, side BC is a diameter and has length 10, and measure of arc AB, so this arc here is 60 degrees. Find the perimeter of triangle ABC. So we can write down everything we know, and we know the measure of angle A is equal to 90 degrees, right? You know the measure of an inscribed angle whose sides contain an endpoint of a circle diameter is 90 degrees. Angle C is an inscribed angle, right? Because its vertex is on the circle, and its sides are chords, right? BC is a chord and AC is a chord. So the measure of angle C equals 1/2 times the measure of arc AB. So the measure of angle C equals 60 divided by 2. That's 30 degrees, right? 30 degrees for measure of arc, for measure of angle C. And that gives the fact that measure of angle A plus measure of angle B plus measure of angle C equals 180 degrees, right? Because the sum of the angle measures of a triangle is 180 degrees. So the measure of angle B is equal to 60 degrees by substitution. So now we're dealing with a 30, 60, 90 triangle, right? So we know the ratios of the different sides, right? So if the big side, the hypotenuse is 10, right? Then AB, this is going to be 10 divided by 2, 5, right? And then AC is going to be 5 times root 3. So the perimeter of triangle ABC is equal to the length of AB plus the length of AC plus the length of BC. And if I put all that stuff together, I get the perimeter of triangle ABC equals 10 plus 5 times square root of 3. So let's do something a little bit harder. Problem 1. So given arc CA is congruent to arc AB, and we have a circle with center O. Prove that triangle CDA is similar to triangle EDB. So let's write down what we know. And we know by the definition of arc congruence in the same circle, measure of arc CA equals measure of arc AB. So we can multiply both sides of the equality by 1/2, right, to get what we have in 4. And we know that angle CAD, this angle here, is an inscribed angle, right? Its vertex is on the circle and its sides are chords. So the measure of angle CAD equals 1/2 times the measure of arc CD. Angle CBD, this angle here, is also an inscribed angle, right? Its vertex is on the circle and its sides are chords, right? So the measure of angle CBD is equal to 1/2 times the measure of arc CD. So we know that these two quantities are equal, right? So measure of angle CAD equals the measure of angle CBD by the properties of qualities, right? By the definition of angle congruence, angle CAD is congruent to angle CBD. And since we're dealing with this triangle EDB, we can just say angle CAD is congruent to angle EBD, right? Because CBD is this angle, right? And EBD is going to be the same angle. It's just, you shorten part of the side, but it doesn't change, the angle. So, angle CDA, so this angle here, is also an inscribed angle because angle CDA's vertex is on the circle and its sides are chords. So the measure of angle CDA is equal to 1/2 times the measure of arc CA. And then angle ADB, so this angle here, is an inscribed angle, same reason, right, as we've been using before. So measure of angle ADB equals 1/2 times the measure of arc AB. And since we know that 1/2 times the measure of arc CA is equal to 1/2 times the measure of arc AB, and we look at what we have in 13 and 14, we get measure of angle CDA equals the measure of angle ADB. So by the definition of angle congruence, angle CDA is congruent to angle ADB. And we can just say that angle CDA is congruent to angle EDB, right? Because angle ADB is this angle and EDB, it's the same angle, right? You just shorten one of its sides, but it's still the same. So we can use the angle-angle theorem for similarity and what we have in statement 18 and 11 to get triangle CDA is similar to triangle EDB. So we're given a circle of center O, segment AD is a tangent segment, and AB is a diameter. Prove that length of CA divided by length of CD equals length of segment BA divided by length of segment AD. So we'll write down what we know, and we know that measure of angle ACB, this angle here, is 90 degrees, right? It's an inscribed triangle, and one side's a diameter, so that's a hint that this is going to be a 90-degree angle. Angle CAD is a tangent chord angle, Why? Because one side is a chord and one side is a tangent segment, right? And the vertex is on the circle. So the measure of angle CAD equals 1/2 times the measure of arc AC. Angle ABC, so this angle here is an inscribed angle. Its vertex is on the circle and its sides are chords. Measure of angle ABC equals 1/2 times the measure of arc AC. So these two quantities are equal, therefore measure of angle CAD equals measure of angle ABC. And by the definition of angle congruence, angle CAD is congruent to angle ABC. By the angle addition postulate and the fact that straight angles measure 180 degrees, we get measure of angle ACB plus the measure of angle ACD equals the measure of angle BCD, which is 180 degrees because it's a straight angle and a straight angle measures 180 degrees, right? So if we substitute what we have in 4 into 11 and we simplify, we get measure of angle ACD is equal to 180 degrees minus this 90 degrees and get 90 degrees. So measure of angle ACB is equal to measure of ACD, right? We see that in 12 and 4. So angle ACB is congruent to angle ACD by the definition of angle congruence. By angle-angle theorem and using what we have in 14 and what we have in 10, we conclude the triangle CBA is similar to triangle CAD. And therefore, measure of length CA divided by measure of length CD equals measure of length BA divided by measure of length AD, because in similar triangles, the measure of corresponding sides are proportional. So that finishes up this video. I hope you enjoyed watching it, and I hope you learned something, and I hope to see you during my next tutorial. All right, take care.